Hi everyone, welcome to part 2 on our video lectures for section 8.4 dealing with trigonometric substitution. In the first video, we were going over the idea of trigonometric substitution. In this video, we're going to be focusing more heavily on examples. So let's take a look at this first example where we're trying to figure out the integral of 1 over x squared times the square root of 4 minus x squared. Alright, so taking a look at this one here, it certainly looks more complicated than the integral that we did in the previous video. However, I assure you that the process itself is not going to be all that different. When I take a look at this integral, I recognize the fact that once more we're taking the square root of a difference of squares. So noticing that, it's a good indication that trigonometric substitution might help. So just as we did before, I'm going to go ahead and begin by drawing a triangle. Okay, so I'm going to go ahead and label my C here, my A, and the B. Okay. So, taking a look at this one here, if we think about the Pythagorean identity, the Pythagorean theorem, we're going to have here a squared plus b squared is equals to c squared. Okay? So, since we have a difference of squares, it looks like we're dealing with the side of a triangle. So, I'm going to go ahead and define a as the square root of c squared minus b squared. Now, when we compare it here to our original integral, or with part of the denominator of the original integral, where we have the square root of 4 minus x squared, well, we get to see here that c squared is equals to 4. So if c squared is equals to 4, then we know then that c is equals to 2. Now what about our b? Well, we have here b squared is the same thing as x squared, so that means that b is equals to x. Okay, now I'm going to go ahead and fill the triangle. We know that c was 2, b was x, and a was the square root of 4 minus x squared. Okay, now we have almost everything that we need here. I'm just going to go ahead and define our sides in terms of trigonometric functions. So for the x, since it's a side opposite to the angle theta, I forgot to put in the theta there. There we go. So we know here that sine of theta is going to be equals to x over 2, which means that x is the same thing as 2 times sine of theta. I'm going to go ahead and put this in blue. And we're also going to have here cosine of theta is equals to the square root of 4 minus x squared over 2, which tells us then that the square root of 4 minus x squared is equals to 2 cosine theta. Alright, now we have almost everything that we need here. The last and final piece of the puzzle here is to figure out what is dx in terms of d theta. So we are going to need a differential. So dx is going to be equals to, so the derivative with respect to theta for 2 sine of theta is going to be 2 cosine of theta d theta. Alright, so now we have our dx, we know what is x, and we know what is the square root of 4 minus x squared in terms of trig functions and d theta. So let's go ahead and rewrite the integral then. So this integral is going to become the integral of x squared, but we know that x is the same thing as 2 sine theta, so we're going to have 2 sine theta squared times the square root of 4 minus x squared, which we know is the same thing as 2 cosine theta, so times 2 cosine theta times, well, it's a dx there, so substituting the dx, which is a 2 cosine theta d theta. Perfect. Now we have our integral only in terms of trig functions and d theta, so we can go ahead and simplify it a little bit. So what I'm thinking of doing here is canceling the 2's, canceling the cosines, so now we're left with a much simpler integral. We're left with the integral of 1 over, well, applying the square here, we're going to have 4 sine squared theta in the denominator. So we have here our integral with respect to theta. So this is going to be the same thing as 1/4 times the integral. Alright, so now inside the integral, we have 1 over sine squared theta. But we know that 1 over sine squared theta is the same thing as the cosecant squared of theta, d theta. Okay, well, lucky for us, we're left with a nice simple integral. The integral of the cosecant squared, if you recall, is the same thing as a negative cotangent. So we're going to have here a negative 1/4 times the cotangent theta plus c. Okay, now remember, are we really done here? Not quite. We still need to figure out, okay, well, what is our result in terms of the original variable, which in this case was x? Okay, so all that we need to do for this problem here is go back to our triangle. How is the cotangent defined? Well, recall here that the cotangent is the same thing as the side adjacent over the opposite. Okay, now notice that for this one here, I'm not using the definition for the cotangent of sine over cosine because I don't want you to mix them up with the way that we're defining the sine and the cosine here. It's easier to think of them, or the trig functions, in terms of the ratios of the side of a triangle. So yes, it's the side adjacent over the side opposite. So that means here that our final answer is going to be a negative 1/4 times the sine adjacent. So the side adjacent was the square root of 4 minus x squared divided by the side opposite, which in this case was the x. So now we need to go ahead and add the c, and there we go. This was our final answer. So for this problem, I went a little bit faster than the first one here, but this problem, at its core, it did not change. We needed to draw a triangle so that we can figure out what is going to be the way that we define the original integral in terms of trigonometric functions. Now, before we move on to other problems, I do want to mention something here with regards to the other trigonometric functions. So notice that in the examples that we've been trying, I've been focusing only on sines and cosines. Whenever I do this type of problems, I usually try to stay using only sines, cosines, and tangents. It is true that we can use secants, cosecants, but sometimes for certain problems they might add a little bit more difficulty, and I like to keep them simple. If I can use only sines, cosines, and tangents, I will stick with them. However, if you choose to use the other trig functions whenever you're working on homework or on exam problems, it's perfectly fine with me. Alright, so let's take a look at another example here. Alright, so for this next problem, we have the integral of 1 over the square root of 9x squared plus 4. Now this one here is slightly different because, well, I still see that I'm taking a square root, but now I'm taking the square root of a sum of squares. So if it's a sum of squares, well then, if you recall the Pythagorean theorem, we're going to have here a squared plus b squared is equals to c squared. So this is going to give me c is equals to the square root of a squared plus b squared. There we go. It's a sum of squares. So it looks like for this problem, we are not given the side of a triangle, but instead we are given the hypotenuse. So let's visualize this. So how will this problem look like? So let's take a look at the triangle. Okay, so this time around, we are given the c. So we're given here that c is equals to the square root of 9x squared plus 4. Now, when we compare it to our original denominator here, it's the square root of 9x squared plus 4. Let's go ahead and figure out our a and our b. Okay, so for this one here, it looks like our a, well, we have here a squared is equals to 9x squared. So that means that a is going to be equals to a 3x, and b squared is equals to 4. So then the b is equals to 2. All right, now before I proceed, I'm going to be doing a little bit of a switch here. Remember in the first problem that we were saying, I mentioned that typically you wanted to have one of the variables defined here with a sign. Now, in this example, if I let my b equals to 2, then it seems like the a would be a 3x, but when it comes time to getting the differential, a negative is going to pop up because of the derivative of the cosine. So I'm going to be doing a switch here. I'm going to go ahead and say that, okay, well, this b here, well, I'll just switch the order, I guess. I'm going to define the a here to be the 3x and the b to be the 2. Now, if you define them differently, it doesn't really matter. You can still get the right answer. Now, with that said, once we have established the sides of the triangle, let's see if we can get our trig functions. Now, one thing to note here is that this problem does have a hypotenuse that has functions of x. It's not as the other ones where the hypotenuse was either 1 or some other constant, so we have to be extra careful for this one. Now, defining the cosine, well, we have that the cosine of an angle theta is equals to the side adjacent, which is 2, divided by the hypotenuse, which is the square root of 9x squared plus 4. Okay, so you see here the cosine function is looking a little bit more complicated. Now, what about the sine function? So for this one here, if I define the sine function as, well, the sine of theta is equals to the side opposite, 3x, divided by the square root of 9x squared plus 4. Now at this point, we might be running into a little bit of trouble because at some point, we do want to figure out our dx, but none of the functions here seem easy to handle once we take the derivative. So what can we do? Well, this is the first example where I'm not going to be using a sine function, but instead I'm going to use a tangent. Because if I use the tangent, well, I know that the tangent is the side opposite over the adjacent, so that way I avoid the complication of the hypotenuse with the square root of 9x squared plus 4. So I'm going to go ahead and define my tangent here as, so the tangent of theta is equals to the side opposite, 3x, divided by 2. So that way I can have an easier function for x. X is the same thing as 2/3 times the tangent of theta. So finding our dx, the x here is going to be equals to 2/3 times the derivative of the tangent, which is a secant squared, d theta. All right, so now that we have established here our trig functions and our dx in terms of d theta, let's go ahead and write the original integral in terms of trig functions. All right, so let's see what we can rewrite. So we have here the integral. Now it was the integral of 1 over the square root of 9x squared plus 4. Is that a way that we can rewrite this one with a trig function? Well, if you take a look here at the way that we define the cosine, we have the cosine of theta is the same thing as 2 over the square root of 9x squared plus 4. So what we can do here is essentially, I guess I'll multiply by 1/2 here, multiply by 1/2. So now I have a 1 over the square root of 9x squared plus 4. That's the same thing as a 1/2 times the cosine. So I'll rewrite it here. The integral should now be 1/2 times the integral of a cosine theta times our dx, but the dx we defined it here as 2/3 times a secant squared of theta d theta. Okay, so let's see, what can we simplify for this one? Well, I think we can cancel out the 2's here, but I also see a cosine times a secant squared. Now remember, secant squared is the same thing as a 1 over a cosine, so we really have a 1 over a cosine squared. Now a cosine times 1 over a cosine squared, we are going to be able to cancel one of the cosines, so we're going to be left with then 1/3, I'm factoring out the constant out, 1/3 of a 1 over cosine. But if it's a 1 over cosine, we know that we can write it as a secant. So we have a 1/3 times the integral of the secant of theta d theta. Now this one here is a nice integral. Hopefully you guys have it memorized. We're going to have here a 1/3 times the ln of the absolute value of secant theta plus tangent theta plus c. Okay, we've done the integral. Now it's time to return to our original variables. So we're going to have here a 1/3 times the ln of the absolute value of a secant theta. Now what is secant theta? Well, in this case, remember the secant theta is the same thing as the hypotenuse over the adjacent, and the tangent is the same thing as the opposite over the adjacent. So let's see what we have here. The hypotenuse was the square root of 9x squared plus 4 over the side adjacent, which was a 2, plus Now the opposite, now in this case the opposite here was a 3x divided by the side adjacent, which is a 2, plus c. Okay. Now, at this point, this is our final answer, but if you're working on the homework, or if you recall that with logarithms, there's many different ways of writing a problem, you might see the final solution represented here in the homework in slightly different ways. I would say that in the cases for exams, you don't really need to worry about, but just for you guys to practice a little bit more of the rules of logarithms, I'm going to go ahead and rewrite this problem in a slightly different form. I'm going to rewrite this one here as 1/3 times the ln of, now notice that we're dividing both terms by 2, so I'll factor out a 1/2 times the square root of 9x squared plus 4 plus 3x. Now at this point, this is where the rules of the rules of logarithms are going to come into play. Whenever you're multiplying two things inside a logarithm, you can rewrite them as a sum of logs. So I'm going to go ahead and rewrite this one here as a 1/3 times the ln of the absolute value of 9x squared, well, the square root of 9x squared plus 4 plus 3x plus, and this is where I'm splitting up the logs, 1/3 times the ln of 1/2 plus c. Now the thing here is, though, that the 1/3 times the ln of 1/2, this is itself another constant. So we can actually just join our two constants here. So our final answer could also be rewritten as the ln, or 1/3 times the ln of the absolute value of the square root of 9x squared plus 4 plus 3x plus some constant c. And there we go. Okay, so this was a problem here where the setup was very similar to all the other problems that we've been doing, but the major difference here was that in order to figure out what we could use as our dx, well, we did not use the sign. Instead, we used a function, or a trig function, that would give us a simpler derivative, and in this case, it was a tangent. Because if we use the sign, then we would have been left with a 3x divided by the square root of 9x squared plus 4, which would have been much more difficult to handle. Okay, so now let's take a look at one more example, but this time around dealing with a definite integral. So let's see. For this problem, we have the integral from 0 to 1 of 1 over x squared plus 1 raised to the 3/2 power. Okay, so this one here, notice that it seems to be a little bit different because at first glance, it might not seem like we have a square root. However, what I would recommend doing first is rewrite the problem so that we have the square root that's actually hidden here in the 3/2 power. All right, so this integral then is the same thing as the integral from 0 to 1 of 1 over, so it's a 3/2 power. So remember, we can always rewrite this one here as the square root of x squared plus 1 raised to the 3rd power, dx. Okay. Now, just as with the previous problems, I notice that I have a square root of either a sum or difference of squares in this problem, namely a sum of squares. So it seems like we are given the hypotenuse for a right triangle. So let's go ahead and draw a triangle. Okay, so let's go ahead and label our C's, our A's, and our B. Okay, so for this one again, since we do have a sum of squares, then we know that C is the same thing as the square root of a squared plus b squared. Now when we compare this one here to our original square root, where we had the square root of x squared plus 1, well, we get to see here that it seems like our a squared is the same thing as x squared, so it means that the a is equals to x, whereas the b is equals to 1. Okay, so label them here. We have b is equals to 1, and a is equals to x, where our c is the square root of x squared plus 1. Okay, so now that we have our sides established here, let's see how we can rewrite them in terms of the trigonometric functions. And for this one here, I'm going to go ahead and begin with the cosine, the side adjacent. So for this one here, I'm going to go ahead and say that the cosine of the angle theta is going to be equals to the side adjacent, 1 divided by the hypotenuse, which was the square root of x squared plus 1. Just going to move this a little bit further down. Okay. Alrighty. Now, what about another trig function that can help? Now, just as the previous problem, I don't really want to use a sine function to help me rewrite the x in terms of a trig function because, well, then we would need to divide by the hypotenuse again. So I'm going to go ahead and use the tangent again. I'm going to go ahead and say that the tangent of some angle theta is the same thing as the side opposite, x, divided by the side adjacent, which was 1. Okay, well, it looks like x is the same thing as tangent, which is pretty good because this is going to allow us to get the dx. So let's go ahead and get the dx now. So if x is a tangent, in fact, I'll do it here, then the dx is going to be equals to the derivative of the tangent being secant squared theta times d theta. Okay? Alright, so we have our dx, we have our other trig functions defined. So let's go ahead and rewrite this integral. Alright, so for this integral, we're going to have the integral of, okay, so what do we have here? Now notice that we said that the cosine was 1 over the square root of x squared plus 1. But this problem doesn't just have the square root of x squared plus 1, it actually has the square root of x squared plus 1 cubed. So what I'm going to be doing here then is cubing my cosine. So if I cube the left-hand side, I also need to cube the right-hand side. So then we can go ahead and rewrite the 1 over the square root of x squared plus 1 cubed simply as the cosine cubed of theta. Okay, so now that we've done this, what about the dx? Well, we said that the dx was equals to a secant squared of theta d theta. Okay, so at this point, this is where we would have performed the integrals before and got our answers just as we did with the previous problems. But this one here, it's a little bit different because now we're dealing with a definite integral. And you guys know me, anytime that I do a change of variables, I like to define my new limits of integration. So what would be my new limits of integration in terms of theta? Well, let's think back to the way that we defined the x. We defined the x to be the tangent of theta. So that means here, if I take the tangent inverse of both sides of the equation, I can get theta by itself. So taking the tangent inverse, we're going to have theta is equals to the tangent inverse of x. Perfect. Now we have an equation for theta in terms of x. So let's go ahead and evaluate our limits of integration. Theta evaluated at x equal to 0 is going to be the tangent inverse of 0, which is 0. So that takes care of the lower limit. What about the upper limit? So evaluating our theta function at 1, we're going to have here the tangent inverse of 1, which is pi over 4. So we're going to have here then the integral from 0 to pi over 4 of the cosine cubed of theta times the secant squared of theta. Now, this one here, since we know that secant squared is the same thing as 1 over cosine squared of theta, we can cancel 2 cosines in the denominator, leaving only 1 in the numerator. So now we're going to have then the integral from 0 to pi over 4 of cosine of theta, d theta. Now, the benefit of doing a problem involving a definite integral is that you don't really need to go back to the original variables, because right now we just have an integral with respect to theta, and we actually have some nice bounds. So I'm just going to go ahead and evaluate the definite integral. So the integral of the cosine is a sine, so we have the sine of theta, and we are going to be evaluating it at 0 and pi over 4. So let's see, we're going to have the sine of pi over 4 minus the sine of 0, which is going to give us, oops, have it to put theta. The sine of pi over 4 is a root 2 over 2, and the sine of 0, well, that's just 0. So it looks like our final answer was simply a rad 2 over 2. Perfect. Alrighty, so this nice example here involving a definite integral is the last one that we're going to be trying for part 2 of our video lectures. Now in the next set of videos, we're going to be going over a few more integrals and an application problem. I'll see you there.